Yes, good afternoon everybody. Welcome to this session of Structural Engineering Design and Detailing. Today we'll be seeing the design of intermediate stiffener. As I had told you what is the importance of intermediate stiffeners. Basically these intermediate stiffeners are provided in a plate girder when the depth of the plate girder is more than 2 meters. So what happens when the depth increases, there are high chances of buckling effect coming into the plate girder. So to resist this buckling, we provide intermediate stiffeners at a different spacing. So that design we'll be seeing today. How important intermediate stiffeners are, what is the importance of end bearing stiffeners, all that we'll be seeing in this video. Today we'll be taking one problem and we'll be designing it. Let us see that. Design an intermediate stiffener. Design an intermediate stiffener for welded plate girder. Whose dimensions are: thickness of the web is 12 mm, thickness of flange is 20 mm, depth of the web is 1200 mm, and breadth of flange is 500 mm. So we have to design also design the connection between flange and web. Let the span of girder be 15 meters. With a UDL of 50 kilonewton per meter. You can just see this question here. Please try to understand the question first. If we understand these, then it will be very clear for us. Design an intermediate stiffener for a welded plate girder. The plate girder is a welded plate girder whose dimensions are: thickness of the web TW is 12 mm, thickness of flange is 20 mm, depth of the web is 1200 mm, breadth of the flange is 500 mm. Also design the connection between flange and web. Let the span of the girder be 15 meters with a UDL of 50 kilonewton per meter. So in this problem he has given all the dimensions. What we'll have to do is we'll have to design only the intermediate stiffener. Sometimes what happens is he doesn't give you these dimensions also. From the start we'll have to design the thickness of the web as well as thickness of the flange, depth of the web, and everything we'll have to design from the start also. Sometimes he can give it like this also, but here he has given the dimensions of the web and the flange. Here only we'll have to provide what is the size of the intermediate stiffener, that we'll be seeing it here. So now let us draw this. Let us see now. Thickness of the web is 12 mm. This is what the thickness of the web is. This is 12 mm. Thickness of the web. And next what is given, thickness of the flange is 20 mm. This is 20 mm. This is 20 mm. Next, depth of the web is 1200 mm. This part is 1200 mm. Okay, and breadth of the flange, this part is 500 mm. So this part, this is what the specific all these dimensions are. Now we'll be designing the intermediate stiffener. We'll be seeing each step one by one, and we'll be solving this problem now. Let us see what is the given, what is given. We'll just write that. Given, he has given us TW, thickness of web, that is 12 mm, thickness of flange, that is about 20 mm, depth of web, that is about 1200 mm, and breadth of flange, that is 500 mm. So all these dimensions he has been given. Now first thing what we'll have to see is, we'll be seeing the spacing of the stiffener. This is a step 1. Please remember this, spacing of stiffener. This is the step 1. Spacing of stiffener, and it is denoted by C. Let us see what is this. Now in page 63 in IS 800 2005, in page 63 he has given us a clause. Page 63, what should be the spacing of the stiffener? He has given this. I'll just read it to you all. You can check here, page 63, IS 800 2007. I request you all to please keep your code books while going through this problem. So in page 63 he has given here design of beams and plate girders with solid webs. In that you can see in the clause number 8.6.1.1, you can see here, when 3D is greater than C or greater than D. You can see here 3 times D is greater than or equal to C, greater than or equal to D. So this is what he has given here. I'll just write this as, here it is given as D should be less than C, and this should be less than 3 times of D. This is what I have just changed this. You just see here, I have just changed the signs. I've got here, it tells that 3 times of D should be greater than C and C should be greater than D. This is what it says. So basically I am just writing it here as D should be less than C and C should be less than 3 times of D. So what does this D mean? D here means is the depth of the web. So depth of the web is 1200. What this clause says is the spacing of the stiffener should be such at a distance such that it should be greater than D. Here D we are taking it as D is dW, that is 1200 mm. Now as per the clause, as the clause says, the spacing of the stiffener should be greater than D. Here the D what we are getting it as, it is 1200 mm. Okay, so I'll just try to increase the spacing of the stiffener. It should be more than 1200. Remember that this depth of the web is 1200. Clause says that it should be greater than 1200. So here I'll just increase the value of C. I'll take it as 1500 C, 1500 mm. So this is satisfying. C is greater than D. D is 1200. C is 1500. So this is satisfied. Now but this should be taken care. C shouldn't be taken such high. It shouldn't increase 3 times of D. Like D is 1200, depth is 1200. 3 times of D will be 3600. If I am taking C as more than 3600, it is invalid. It doesn't come up with the clause. So it should be taken up somewhere which it should suit this clause. It can be taken as 1500 or 1800 or 2000, but it shouldn't be taken such high it is crossing these limits. So this is the first thing what we'll see. This is the spacing of the stiffener. It is given in page 63, clause 8.6.1.1. Clause, this is clause 8.6.1.1 in page 63 IS 800 of 2007. So this is very simple. We have already got the depth of the web, and that we are just increasing the spacing. How much should we increase? It should be greater than depth of the web. Depth of web is 1200 and this is 1500. I'll just write it here. You can understand what is this. 1200 is less than 1500 and 1500 is less than 3600. D is less than C, C is less than 3D. So just understand this is the spacing of the stiffener. Hope this step is very clear. It is very simple. Next we'll see what is the next step. We'll be seeing that step now. We'll just check that step now. Let us check the next step now. This is the first step. We'll be seeing spacing of the stiffener. Let us see the step 2. Remember, this is outstand of the stiffener. Outstand of the stiffener. Even this has been given in the clause in page 65. A clause has been given. I'll just read it out to you. In page 65. Page 65 of IS 800 of 2007, 8.7.1.2. See, what does it say? What does it say? Unless the outer edge is continuously stiffened, the outstand from the face of the web should not exceed 20 TQ epsilon. 20 TQ epsilon. So the outstand of the stiffener shouldn't be taken greater than 20 TQ epsilon. When the outstand of the web is between 14 TQ epsilon and 20 TQ epsilon, then the stiffener design should be on the basis of a core section with an outstand of 14 TQ epsilon, where TQ is the thickness of the stiffener. So basically what the clause says is we shouldn't, it is between, basically it is between 14 TQ epsilon and 20 TQ epsilon. The clause says that the outstand of the stiffener shouldn't be greater than 20 TQ epsilon, but here for all practical calculations we will be taking it as 14 TQ epsilon. Now you must be imagining what does outstand of the stiffener mean. See, what is happening is if this is our plate girder. See, this is our plate girder, this is my web, and this is my flange, and this is my web. What basically I am trying to do is I am trying to provide a stiffener somewhere here. If this is my stiffener, I am providing, this is my stiffener. This is my stiffener, vertical stiffener, which I am providing it here. Now what is happening is, what I want to see is spacing I have designed. Spacing is somewhere 1500 mm, which I have got from the step 1. Now what I want to see is the outstand of the stiffener. That is how much the stiffener should come outside. How much should it come outside? See, this is my cross section, which is seen as I section. But what happens is, if you just turn it into other view, what happens is the outstand, the stiffener comes outside. The stiffener comes outside. Now we want to know how much outstand of the stiffener that should, how much outside should it come. That is what is outstand of the stiffener is. So for all practical calculations, we will be taking it as 14 TQE. Remember this, it shouldn't be greater than 20 TQ epsilon. So what we will be seeing, TQ is the thickness of the stiffener. Here I will be assuming the thickness of the stiffener as 8 mm. Later on, if the section fails, we will have to increase this only. We will have to increase the thickness of the stiffener here. So basically I will be going with 8 mm thickness of the stiffener, and we will try it out at the last level where we will be checking whether it is sufficient or not. We can know this. If it is not sufficient, we can just change this thickness of the stiffener. Let us calculate it here. So for all practical calculations, outstand of the stiffener will be taken as 14 TQ epsilon. As I had told you, it should not be greater than 20 TQ epsilon. So what is TQ? TQ is the thickness of the stiffener. Here I am assuming it as adopt 8 mm thickness. thickness of stiffener, that is TQ is equal to 8 mm. Hope this is clear. It is 8 mm. I am just adopting it as 8 mm. I will be seeing it in future whether this is sufficient or not. If it is not sufficient, we will try to change it all. We will just check it here now. 14 TQE. So this is 14 into TQ is 8. As you know, epsilon is root of 250 by 250. So 14 is, this is 14 TQE, thickness of the stiffener. I'm assuming that thickness as 8 mm. I'm just substituting it here. 14 into 8 into root of epsilon, as you know, it is root of 250 by 250. I've just substituted these values here. After calculations, I'm getting this value as 112 mm. 112 mm. So this is outstand of the stiffener. This is how the stiffener will come, 112 mm outside the plate girder. This is, as we are seeing it in a cross section, it looks like this, but when you see in another view, you can see the stiffener coming outside. That is about 112 mm. It will come outside the web, outside the web. This is what first step we had seen, the spacing of the stiffener. As you had seen, it should be greater than the depth of the web. If the depth of the web we had got it as 1200, we have to increase it. It should be more than D. So we had spacing of the stiffener, we are denoting it with C. So we have increased it to 500, but it shouldn't be greater than 3 times of D. So we took it as 1500. After that, we are just seeing what is the outstand of the stiffener from clause page 65, clause 8.7.1.2. We have got these values. It shouldn't be greater than 20 TQ epsilon. I have taken it as 14 TQ epsilon. It should be, for all practical reasons, this will be used. I've just adopted the size of the stiffener as 8 mm. I've just substituted here. So this is the outstand of the stiffener, which I'm getting it as 112 mm. So hope this step is also clear to you all. We'll be proceeding to the next step, inshallah. Now let us see the next step, step 3. Hope these two steps are clear to you all. Sometimes in some questions he will not give you the depth of the web and all these dimensions. In that case, I request all of you all to please follow the first design of the plate girder which we had done. Now let us see the step 3 here. Step 3, moment of inertia to be provided. We'll have to check this now. Moment of inertia to be provided. We'll have to check this here now. What is the moment of inertia we'll have to provide? Okay. Let us check this here. What is the moment of inertia to be provided? Basically what happens is what we are providing and what is the moment of inertia exactly to be got. We'll be calculating that here. If the moment of inertia provided is greater than the calculated moment of inertia, then it is safe. If we are providing lesser moment of inertia, then there are high chances of this failing away. So now we'll be seeing this now. Let us see this. 112 mm, and as this is the outstand of the stiffener, I'll just check it here. 8 mm, 8 mm. You can just see this. See, you can understand here 112. This is outstand of the stiffener, and same thing outstand of the stiffener. Now this part you might be thinking, what is this part? This is 12 mm. This is thickness of our web. This is thickness of the web, 12 mm. This is outstand of the stiffener. This is outstand of the stiffener, and this is thickness of our stiffener. So here, what is the moment of inertia provided? We'll be seeing this as BD cube by 12 minus of BD cube by 12. Now what is this B? What we'll have to see is here, just see here, T cube D cube by 12 minus of this is thickness of web. You can see thickness of web. TW is thickness of the TQ into, you can just check it here. Just check this here. It should be TQ TW cube by 12. See TQ, this is thickness of the stiffener as we had adopted it as 8, and D will be seeing what is the total depth here by 12 minus TQ is again the thickness of the stiffener and TW is thickness of the web. I'll just substitute these values and we'll be seeing what is the moment of inertia we are providing here. So TQ, as you know, it is 8. I'll just substitute these values here. 8 into, now just see here, D cube, capital D. We'll have to take this D whole, 112 plus 12 and 112. So see 112, this is the outstand of the stiffener and both the sides of the web it is coming out, and 12 mm is the thickness of the web. If you can just total it, it is 236 here, 236. 8 into 236 cube by 12 minus of again TQ, this is 8 into thickness of the web, 8 into 12 cube by 12. You must have understood till here. It is very important here. Moment of inertia, one will be providing it. Next we will be calculating the moment of inertia. If the provided moment of inertia is greater than the calculated moment of inertia, then it will be safe, or else we will have to change the moment of inertia here. So how am I calculating this? BD cube by 12 minus BD cube by 12. This is the whole thing. What I am taking it as B. B I am taking it as TQ. That is the thickness of the stiffener. That is 8. I have substituted here. D cube. This is 112 plus 12 on 112. That is 236 cube by 12 minus 8 into 12 cube by 12. If you calculate this, I am getting this value as 8761.68. 8761.68 into 10 cube mm4. This is the I provided. This is the moment of inertia provided, 8761.68 into 10 cube mm power 4. This is the value what I have got here, moment of inertia provided. Let us check that with the moment of inertia calculated. If this moment of inertia provided is greater than moment of inertia calculated, then most probably a section will come into the safe limits. If this doesn't come under that, then we'll have to change the moment of inertia and we'll have to provide the moment of inertia what we are calculating here. Let us check that here, moment of inertia calculated. Moment of inertia calculated, we'll just check this here, page 67, 66 and 67. You can just get it here in page 66 and 67. There is a clause given here. I'll just read it out to y'all. Page 66 and 67. See, it tells here, in page 66 and 67, we have two clauses here. What is the moment of inertia? It says that if the C by D ratio is less than root 2, if it is greater than root 2, you have moment of inertia calculated as 0.75 d TW cube. And if the C by D ratio is less than 2, then we have the moment of inertia calculated formula as 1.5 d cube TW cube by C square. I'll just write this clause here. It is in 8.7.2.4. Clause 8.7.2.4. Just see here, what does this clause say? If C by D value is greater than or equal to root 2, then IS, this is calculated moment of inertia, should be 0.75 into d TW cube. And if C by D is less than root 2, then IS is equal to 1.5 into d cube TW cube by C square. You just see here these two and where D is given as the depth of the web and TW is the minimum required web thickness for spacing. You can see here D is the depth of the web, means D is DW and T is thickness of the web. And C is the actual spacing of the stiffener. C is the spacing of the stiffener. We'll just substitute these values and we'll check it out what is coming. C by D. First we'll have to know what is C by D. C is 1500 what we have got here. 1500 and our D is 1200. So after calculating this we are getting it as 1.25 is equal to 1.25. 1.25, is it greater than or equal? It is less than root 2. 1.25 is less than root 2. Okay, hope this is fine here. I have just calculated these values here. C by D. There are two clauses have been given. If C by D is greater than root 2, we'll have to provide moment of inertia 0.75 d TW cube. And if it is less than root 2, C by D is less than root 2, moment of inertia IS will be 1.5 d cube TW cube by C square. So it is very important, we'll have to check these values. What is C? C is the spacing of the stiffener, that is 1500 as we had calculated earlier. And D is the depth of the web, that is 1200. I have just calculated, I have got it as 1.25, which is less than root 2. If it is less than root 2, what we'll have to take? We'll have to take this value of 1.25 d cube TW cube by C square. After substituting these values, now we'll have to check if the moment of inertia what we are calculating is greater than the provided or less than the provided. If it is greater, then we'll have to take this value. If the provided moment of inertia is greater, then we'll have to take that value. So we'll just check these values here and we'll proceed further. We'll check that now. We'll just substitute these values and we'll check what are we getting. We'll have to use C by D is less than root 2. We'll be using this moment of inertia formula. We'll be using this here now. Okay, let us substitute this value here and let us check what is the answer we are getting. So IS is 1.5 into D cube. As I told you, D is the DW depth of the web. We have got it as 1200. I'll just substitute that 1200 cube into TW. This is the thickness of the web. Thickness of the web, it was given in the question, that is the thickness of the web is 12 mm there. 12 mm, 12 cube by C square. C is the spacing of the stiffener, that is 1500 square. 1500 square. After substituting these values, the answer what I am getting it as 1990 10 cube. 1990 into 10 cube mm to the power of 4. So you can just check this here, 1990 to 10 cube mm power 4. In the moment of inertia provided, we had got it as somewhere 8761.68 into 10 cube. So it was very much greater than this value. So moment of inertia what we were providing, it was very much greater than the moment of inertia calculated. So we can proceed with that moment of inertia which we had provided in the previous step, which we had calculated in the previous step. Hope this is clear till here. For step 1 was the spacing of the stiffener, that is we'll have to increase it more than the depth of the web, and it shouldn't be such greater that it is exceeding 3 times of D. So we had taken it as 1500 as the depth of the web was only 1200 and it was not exceeding 3 times of D also. Next what we had done, the step 2 was outstand of the stiffener, that we had calculated from the clause it shouldn't be greater than 20 TQ epsilon. We had taken it as 14 TQ epsilon. So TQ we had assumed it as 8 mm thickness of the stiffener. We had substituted that value, we got it as 112. After that, next step what we had done is we have just calculated this moment of inertia, provided and calculated. So whatever we are providing, it should be greater. So from the calculation, the provided moment of inertia we are getting it many times, about 3 to 4 times greater than what is calculated moment of inertia. So hope I hope this session is clear to you all. I request all of you all to please keep practicing these problems. It is not so easy. You just can't understand these problems in a day just before an exam. I request you all to please go to these problems again and again and try to solve as many as possible. See, once you come across, if you try solving these problems, you might come across some, you might get stuck somewhere. So once you get stuck somewhere, you can please ask me doubts there. Once I clarify, you will be confident enough and you can solve any problems. So I request you all to please go through this session. I'll be continuing this problem in the next session. Hope this session was clear to you all. If you have any doubts, please try to comment in the comment section. I'll try to clarify all your doubts. Thanks a lot for this session. Thank you.